Hi, Amy. How are you doing?
Hi, sir. I'm good, thank you. How are you?
Very good, very good. So, did you get some time to work on mechanics?
Yes, I did. Was working through a couple of the questions, and the principle that you taught me yesterday all applied. So it was actually nice and easy for me.
That's
I
very
haven't
good.
finished all of them yet, but just working through it. But I think I got the general concept.
That's excellent. So, in today's lesson, what I'll do is take three examples, which are actually common examples for the situation where forces are applied to a system and we have equilibrium position,
Okay.
or we could have a position where the equilibrium state is not there. In that case, there'll be an acceleration.
Mm-hmm.
Now, when external force is there, external force is not equal to zero, but there is a net force. In that case, the object is going to move with the acceleration. And that is where the second law of Newton applies.
All
And
right.
so we'll take up examples based on second law of Newton today. Okay?
Okay.
Let
Yep.
me share with you the screen and then we'll discuss more about it. So, Amy, as I was saying, we'll discuss applications based on Newton's second law of motion. So, here are three very common examples which are always seen. One, I'll treat this as my example number one, where we have two mass on a table. We'll
Mm-hmm.
assume that the coefficient of friction is kind of negligible between the masses and the table.
Yep.
Now, when we have a system, there could be two masses or n number of masses, but they are all on a table and they are attached by a string. That is one thing. Second case could be that we have a pulley on the side, as you can see here, and one of the mass is hanging, right? So there is a gravitational force which pulls it down, and that will set the system in motion, right? So there's
Yeah.
external forces because of gravity. In the first case, we actually apply an external force, which I have mentioned as F of P, Fp. External force is applied to pull it, and then we have an acceleration. So that is how the system will be in a constant acceleration. Now, and in the third case, we'll take example where we'll take up a pulley, right? So in a pulley, we can have two masses attached to a string, and these two masses being of different mass. In that case, they will exert different force, and there will be a motion. Greater the mass, it will pull more, and then it will move the whole system with some acceleration. So in all these three cases, they are kind of related, as you can see. In first case, we are applying an external force. In the second case, the external force is applied, and that is because of the gravity. And
Yeah.
in the third case, we do have differences mass and it's a pulley system, which works. Most of the examples in your book are actually based on these three examples. There could be some
All right.
variations. Yeah. Once you understand all these concepts, it'll be very easy for you to actually sail through this section. And then we'll
Okay.
move forward. Okay.
Yep. Thank you.
Now, before moving forward, let's actually review what is the second law of motion and how does it relate mass and acceleration. As we discussed earlier also, whenever we model a physical situation, a real life situation with mathematics, we take some assumptions, right? So we'll
Yeah.
look into those assumptions. We'll also make a free body diagram before really getting into equations and solving them. And then we'll take up our examples one by one. Okay?
Yep. Sounds
Let's
good.
begin. Yeah, let's begin with the Newton's second law. As you know, here is what Newton's second law is. Can you please read this law for me?
Yep. The acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. The direction of acceleration is in the direction of the net force acting on the object.
Perfect. So the net force is being represented by sigma f. It really
Mhm.
means that we'll actually translate all the vectors at a point, right?
All right.
And all the tails will be at this point. From
Yep.
there, we'll resolve the forces into x and y directions and see what is the net force. Now, if this net force is equal to zero, if the net force somehow is equal to zero, in that case, we can see very clearly that A will be equals to 0 over the mass and acceleration will also be 0, correct?
Yeah.
No acceleration. That is
Right.
the state of equilibrium.
Oh, okay.
So those type of examples we have seen earlier. Now in
Mm-hmm.
this particular case, we have a net force F which is going to be greater than 0. Since it is greater than 0, the value of MA will be greater than 0 and we expect a positive value for A. A will be greater than 0. Okay. So that is the situation which we are looking into, correct? So let's also, so I hope you have understood this equation, which is A is directly proportional to the net force and inversely proportional to the mass.
Mm-hmm.
Now, how does this second law actually relate mass and acceleration? So let's understand what is 1 kg. Can you please read what is this 1 kg written here?
1 kg is the mass which will undergo an acceleration of 1 meter per second squared when a force of 1 Newton is applied to it.
That is the definition. Many times in the test paper, this could be the definition of your prime interest, right?
Oh, right.
Okay.
Mm-hmm.
Now this part, can you please read this also?
From Newton's second law, we can find the effect of net force and the mass on the acceleration of the object.
Right. That is how it relates, right? So F equals
Yeah.
to ma. So we use this equation either way. Acceleration is net force over mass, or net force is mass into acceleration of the whole system. Is that clear to you?
Yeah.
Now let's also look into the assumption. When we took few examples, as you saw right in the very beginning, we are talking about a system where we have different masses which are attached by a string. We could have a pulley also. So let us see what kind of assumptions should we make when we describe this kind of a system. So can you please read all these assumptions one by one?
Right. When a flexible cord pulls an object, the cord is said to undergo tension, and the force it exerts on the object is the tension Ft.
Right.
Cord is inextensible, with negligible mass, and a flexible cord can only pull and cannot push an object.
Correct. Now, what is a light object? When we say in a question, this is a light object, what does it mean?
Mass of the object is negligible compared to other masses. The force exerted at one end is transmitted undiminished to each adjacent piece of cord along the entire length of the other end. Tension is the same at both ends of a light string.
Perfect. And what do we understand by inextensible string?
It's a string that does not stretch,
Mhm.
and the acceleration is the same in objects at both ends of a light string.
Perfect. Now let's talk about the pulley.
So a pulley has no mass, neglect rotational inertia, and tension is the same on either side of the pulley.
Correct. So these are important things to consider when we model the physical situation into mathematical models, right? Now let's take our
Yep.
example where we have a mass and another mass is hanging from a pulley. Now, because of this hanging mass, it is under an external force due to gravity. And therefore, there is an acceleration, A. And this acceleration is same for both the masses since they are attached by a string, correct? Can you please read this question, which we are going to
Yeah.
now answer?
All right. So two boxes with mass M1 and M2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley as shown in the figure. Find general expressions for acceleration of each box and the tension in the cord.
Correct. So actually speaking, all the three examples which I have taken, they have the same statement where we'll have two masses, right? And we'll try to figure out what is the acceleration of each mass and what is the tension in the cord, right? Only thing is the three
Yeah.
situations are slightly different. In the first situation, we had two masses on a table. In the second, one on the table, the other one is hanging. And in the third, both are hanging and the pulley in between. So they are very much related to one another. And therefore, our solutions, as we gradually move from one to the other, it will be very clear to you. When we add complexity to a question, how does the thing change? And two things which we are very
Mm,
interested in are acceleration and tension. So once we understand in these
right.
three, we could actually scale it to any question. That is the beauty of these
Oh, right.
examples. Okay. Now,
Yeah. Wait, so only two and three of the out of the three that you showed, only two and three use a pulley.
yes, yes, we are using pulley for only two and three. The first one
Okay.
is the straight up where external force is applied to move it, right? It's like, kids
Okay,
play with
okay.
the toys and they just pull something and it
Pull
moves.
it. Yeah.
So those were the examples which we
Okay.
did
Yeah.
earlier. Now, let's look into
Right. Yeah.
where external force is there. Now, in this case, we have to look into a system one by one. So let's look into this particular section where the mass is hanging. Since M1 is
Hmm.
hanging, it does have a weight, and this weight is a force which is pulling it down, correct? And the force is M1G. Now, since the system moves down with an acceleration of A, as shown here, right? Therefore,
Yeah.
you see that the net force is positive, right? Net force is not
Right.
zero in this case. What is the net force? Net force for us is the difference between the downward pull due to gravity on this mass and the tension in the string. The tension is always
Oh,
in the opposite direction. Therefore, we wrote
yeah.
the equation m1g minus ft. That is the net force. Now, this net
Hmm.
force, according to the second law of Newton, should be equal to mass into acceleration. Mass
Yeah.
on acceleration is a, and so we get our first equation. Is that clear to you?
Yeah. That's clear.
And this is our free body diagram, which clearly indicates that we do have a mass m1, force downward is m1g, ft is the tension, a is the acceleration on this string.
Oh,
Correct?
yeah. Yeah.
We have seen that this string is inextensible, right? And
Hmm.
this string will have a tension force which is f of t in the opposite direction. Because of the pulley, it will be transmitted to the other end of the string. Same value, correct?
Mm.
Because it has
Yeah.
negligible mass. It has
Right.
negligible mass. And same value, f of t, that tension pulls the second mass. And the acceleration remains same because the system is supposed to have a negligible mass, correct?
But
So,
the
yes.
sorry, the thing
I
that I
mean,
didn't get was,
yes.
yesterday when you explained me with the pulley and it having no mass, you said when you like pin it on the wall, let's say something like that in the center, it's
Yeah.
not going to have any mass because the pin is like holding it. But in this case, since it's like almost hanging off the thing,
No, no,
where
this pulley is in a place, it is like pegged
oh
down.
fixed.
Yes, yes. Pulley is fixed to
Oh,
the table, and the rope is going over the pulley.
all right, okay,
So it's a similar
okay, yeah,
situation, right? So rope is going
yeah,
over,
yeah,
and therefore we have this Ft. So on the second mass, you can see very clearly there is external force Ft, and this external force causes the acceleration A, and therefore the equation will be Ft, the tension, is equal to m2a. So that becomes our
hmm,
second equation.
yeah,
So we got these two equations, and to get acceleration and tension Ft from these two equations, very simple. If I add these equations, Ft and Ft will cancel, and we'll get
uh,
m1g equals to a times m1 plus m2, correct?
yeah.
And then all the things are known to us, the two masses, the gravitational force, acceleration will be equals to m1g divided by m1 plus m2, correct?
Plus M2, yeah.
Once you know acceleration, you can find ft because ft
You
is
sub it in.
nothing but m2 times a. So just multiply by the second mass to get the force due to tension. Is that clear to you?
Yeah. So it's kind of like forming just two like simultaneous equations and then
Solve.
working from there.
Yes.
Oh, okay.
Now here is what I was saying. I just typed out the whole solution. So what we discovered was due to m1, which is hanging, there is a force of gravity, and that is the external force.
Yeah.
m1g minus the tension is equals to m1a, where a is the acceleration. And this tension is applied to the second mass, which is on the table, which also moves with the acceleration a. So f of t is also equal to m2a. If I add the above two equations, in that case, what do we get? We get that m1g is basically equal to, let me write m1g here, because ft and ft will cancel, is equals to m1a plus m2a, or m1g is equals to m1 plus m2a. We have taken it common, right? And then we
Yeah.
divide by the sum of masses, and we get the acceleration, which is mass 1 divided by sum of the two masses into gravitation force. So that
Yeah.
gives a general formula to find acceleration in a system where one mass is hanging and the other one is on the table. Is that clear to you?
Oh. So okay, I know you have to like do it that way, but if I just went straight to the formula, is that
Yeah,
just so much easier then?
yeah, it
I
is.
understand it though. Yeah. Okay.
At the end, I'll give you a summary of the formula for all the three. Once you see all the three formula together, it'll make so much of sense for you. I'm telling you.
Yeah. All
Another
right.
thing, now ft, is m2 times a. So we'll just multiply the acceleration which we calculated with the mass of the second object, and we get our formula: product divided by sum times gravitational force. You see, product sum divided by g.
Yeah. Yeah.
So F is mass
Oh.
into acceleration, right? Acceleration is
Yeah.
gravity. And the mass is like product and sum in this case.
Oh, I see.
Very
Yeah. Yeah.
important to remember. And since you know F is ma, you could go back to A also, which is
Yeah.
m over m. You understand?
Mm-hmm. Yeah.
So
Yeah. I
once
do.
you have all these formulas on your sheet and you look at them and try to understand, the concept will be absolutely clear. So with this, I think it's very clear how to do this, correct?
Yep.
Let me give some values to these two masses, and let's actually calculate what is acceleration and what is the tension in the string. So what I've done here is that I've just extended this question, and I'm saying let the mass m1 be 6.0 kg and mass m2 be 4.0 kg. So I know acceleration is this formula and tension is the other formula. We'll just substitute the values 4 and 6 in the formula and calculate with gravity as 9.81, right? So once you multiply,
Yeah.
you get acceleration of 5.886. Now, what should be the significant figure for your answer?
Sorry, it kind of the Wi-Fi broke up.
Okay, so now here, what I'm doing here is whenever you work on these examples, you should know to what accuracy you have to write your answer. So
All
normally
right.
it's not mentioned. In that case, you
In the
should
question.
oh, yeah. But in this question, we
Yeah.
have written exactly what we are looking for. So we have said that it should be accurate to one decimal place, right?
Oh yeah.
If the
Yeah.
statement was not there, then you
How
should
would I know?
two significant figures.
Oh, okay. Yeah, didn't you say yesterday with whatever values are given in the question, whatever significant figure is given in the question, if that is not stated, then you just do it in that one.
Yes, yes, that's what I
Oh,
said.
okay. Yeah.
And now in this case, we have said one decimal place, so round it to one decimal place.
Okay. Yeah.
5.889 as rounded to 5.9 meters per second square. And for tension, I just multiplied the acceleration with the other mass, m2, and got my answer as 23.54, rounded to one decimal place as 23.5 newtons.
All right. Yeah.
Units and accuracy is very important when you write your answers, right? That ensures.
Yeah.
Correct. Now, let me take the second example. Is this all absolutely clear to you?
Yes,
The
it is.
right? Very good.
Yeah.
Now, let's take the second example. We'll hang both the masses on the pulley. So both are
All
hanging.
right.
The question is still the same. Can you please read the question?
Yep. Two boxes with mass of m1 and m2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley, as shown in the figure. Find a general expressions for acceleration of each box and the tension in the cord.
Simple as that. Basically, all the questions in your book are saying the same thing. They're writing the statement in a different way. There are two passes. Either they're hanging with this pulley, or one pulley and one table, or both are on the table, right?
Okay.
That is it. So
Right.
once we do these examples, things become so simple. So
Mm.
clearly in this case, one mass is more than the other, both are hanging, so there is an acceleration. M1 is greater than M2.
Yeah.
Let us assume this, right? So we'll draw a free body diagram. That is always the first thing to do. So if you look at the first mass, you know the gravitational force pulls it down, and that is your net force. That is the force downwards. The Ft is the tension, which is going upwards. Difference of these two is the net force, correct?
Yep.
So the net force, F net, let me write, sometimes we write F net or sigma F is m1g minus Ft.
F
That causes
T.
an acceleration of A, and therefore it is equal to m1a. So we get our
Oh,
equation for 1, exactly same as what we did earlier.
yeah.
Second mass
Mhm.
is, however, hanging. It is not on the table. Since it is hanging, it also has this mass m2g force acting downwards. Correct?
Oh, yeah.
The tension is upwards and tension is taking it up. So we are putting this up as positive direction. So the net force here is Ft minus m2g. Acceleration is A, same, since the string is inextensible and it is
Mm.
a very light string. So that is equal to
That's
m.
clear.
So again, the same
Yeah.
equation. You can actually add these equations and these cancel, and you can now find what A is, correct? Once you find
Yeah.
A, you can find what Ft is, correct?
Yeah, I
That's
like that.
the process. So let's move
Oh,
on.
so is it, yeah, it's the same process. You just need to be aware of what is actually happening, like in the diagram, because you know that you can't just write like we did before, force
Yes,
equals ma, because you can see there's it's not on a table. It's like hanging
yes,
again, so there's gravity acting on it. So you should be aware that something else has to like act on it. So you
correct,
can't just write the same thing. Yeah, that makes
correct,
sense. Yeah.
correct. So I'd like you to, Emmy, read this kind of summary here. Read this part.
Okay. So, system of equations. Boxes are moving in different directions, and so we will consider two systems.
Very
They
important.
will, all right.
We
Yep.
are moving in different operations. You cannot treat everything as one system. In the
Yeah.
first example, both were on the table. They were both moving in the same direction. We could have just clubbed both the masses together and written one equation. You remember that part?
Yeah.
Here, you cannot do it. They are moving in different directions. And therefore,
Oh.
yes. And so, once again, read this part.
Okay, so boxes are moving in different directions, and so we will consider two systems.
Correct.
Oh, so before it was working in one direction, so we can use it as one system. Oh,
Yes.
I get it. Yeah. They will have the same acceleration and tension because of flexible, inextensible string and the light pulley. Oh,
Correct.
so these assumptions we made. Oh, okay.
Yes. Same equations which we discussed earlier on the first system, which is m1g minus the tension Ft is
Yeah.
equal to m1a. And in the second case, Ft minus m2g is m2a. When we add the above equations, what do we get? The Ft and Ft part cancels, correct? So this
Hmm.
cancels, and we get m1g minus m2g equals to m1a plus m2a, taking g common and a common, and then dividing, we get the expression for acceleration. Is that clear to you?
Yeah. Yeah.
So in this case, we have difference of the masses on the top divided by the sum times the gravity. Is that clear?
Yeah.
Now, we can substitute the value of A and find the tension. Let's go to the next page and see our calculations. So we just calculated that the acceleration is difference of masses divided by the sum of masses times the gravitational force. We also had these two equations with us, correct? Uh, and now, from the second equation, I can actually rearrange the second equation, correct? Taking, let me just go one by one. So m1g minus ft is m1a, taking m2g on the right hand side, we get ft, which is the tension force, is m2a plus m2g. Now substituting the value of a, which we just calculated, we can simplify. So both have g common. So I factored out g, right? And
Yeah.
then wrote m1 minus m2 over m1 plus m2, right? Like, in fact, I've done the calculation here once again, and then, just go straight from here to there, correct? So we have g common, right? So g is common, and plus 1. So you just simplify taking common denominator. And once you do that, M2 and M2 and minus M2 and plus M2 cancel away. You get 2 times M1 in the numerator. So 2 times M1 times M2 in the numerator now with sum of the masses in the denominator times gravity. So that becomes the force of tension.
Yeah. So it's just the same as the other one, just that there's a 2 in the calculation on the numerator section.
You see there's 2 tensions F2 going up, 2 twice.
Oh,
Twice.
yeah.
So the tension is doubles up because
All right.
both are acting up. So it makes sense, correct? So
Yeah.
you must have seen so much of correlation between the examples. So I thought, let me summarize. But before that, let me again take some values for M1 and M2 and calculate the result. So in this particular example, I'm saying let M1 be 6 kg, M2 be 4 kg. And then I'm saying, well, let's calculate. Now, I'm not writing anything for rounding. So what should be the answer rounded to?
So in the calculation, we're given it's to one significant figure?
Yes.
No, 2. 1? Yeah, it is one significant figure. So why is the question in?
It should be 50 rounded to 50. Yeah.
50?
Yeah.
Oh. That's why I was confused because I saw the 2 and I was like, oh, that's right. So then I was like, yeah.
Important, right? You got it. So if I don't write anything,
it's a good test on me.
One significant figure.
Okay.
Just do simple calculations which are shown here. Plug in 4 and 6. 4 and 6 also is a good number, right? Because 4 plus 6 is 10. So you just divide by 10. It's so simple. I'm taking values which are very simple to work with.
You're just trying to make me understand the concept. Yeah. Yeah.
And then round this to one significant figure, which is 2, and round this to one significant figure, which is 50, right? Do you get the idea?
Yeah.
So not 47. Yeah. 47 will be a wrong answer.
All right. Yeah. It's weird though, because even in the exam, even if you just miss Newton's, like 1 mark is gone. Don't do it to 2. If you do it to 1, like it's supposed to be 1 and you do it to 2 significant figures, mark gone. And that's the difference between a whole grade sometimes. So like you can't really afford for that. Yeah.
Got it?
Wow.
Very good.
Yeah,
so
got it.
It's very important to put in the values, check your answer, be careful why there was a difference in answer, look into the significant figures and then figure it out. This is something very critical to work with, right? After doing all the labor in solving the question, if you write the answer incorrectly, you lose so many marks.
Yeah, and it's pointless after that because that was hard work. Yeah.
So, Amy, here is the summary for you. So what we have done today is we have looked into these 3 types of examples, right? So the first one we took earlier, and it was the same question. There are 2 masses, M1 and M2. Situation is slightly different. We are only interested in finding the acceleration and the tension in the string, correct?
Right, yeah.
All our assumptions were same. Flexible, light string, correct? That was our assumption. So in the first case, you found that external force was applied, and this external force was Fp.
Yeah.
And therefore, the acceleration was force divided by total mass, right? That is Newton's second. Force divided by total mass. That is acceleration. In the second case, this force was not applied externally by you, but it was because of the gravity, correct?
Right.
M1g. So you see the numerator is what? M1g. So this force Fp is being replaced by M1g. Equation is same, divided by M1 and M2. You see that?
Yeah.
Because the force applied now, F of P, is M1g because of the gravity, this hanging object.
Right.
In the third case, again, it is mg, but the net mass effect is there are 2 different masses on the other side. So it is M minus M2. You get the idea.
Yeah, and then you still multiply by g because gravity is still acting on it.
Correct. Divided by M1 plus M2. Done.
So whenever there's a pulley, can you just say whenever there's a pulley, you have to be aware that gravity is acting on it?
Yeah, of course.
Can you say that? Okay.
Both the masses are just hanging, right? And the gravity is acting on both. So the net effect is M1 minus M2. That is why they move.
Right.
So all the 3 formulas are actually the same. Fp is the force being applied. Maybe you applied externally, or maybe because of the difference in masses.
Gravity. Oh, yeah.
So that force is in the numerator, F of P, and divided by all the sum of the masses.
And that's the same for all of them. You're dividing by the
All the
sum
three.
of the masses.
All the three.
Oh,
Got it?
yeah, I did. That's clear. So, but I think the key point that I didn't know before this lesson is because you really stressed it. You know, where you said it, especially with the pulley, because they're acting in opposite directions.
Yes.
You need to be aware of that. Whereas with the first one, they're acting in the same direction, and the second one, they're acting in the same direction. So you use that as one system. Whereas with the pulley, the last one, you have to use two systems.
Correct. Now, let's talk about the tension. Tension is M2A, right? The second mass we'll always consider, and if there are many, consider the last one.
Last one,
put 10, consider the last one. This is so simple.
10th one.
The tension is
Yeah.
same. Tension is
Yeah,
same.
yeah.
So it is same tension and same acceleration. Just consider the last mass, M2A. That is the general form.
That's working out, yeah. Because if you did the first one, you'll have to subtract the one pulling force from the tension.
Go to the last one.
Yeah.
Correct.
Right.
You know what acceleration is because you calculate, multiply with the last mass. You get your formula. So here, Fp times M2, you get your formula. Second case, M2A is my tension, correct? So, so what I did was, we have this acceleration M1. I just multiplied by M2, correct? M2 times A, I know, right? And in the third one, it is important to understand it is twice M1 and M2 because there are two strings and two tensions.
And that's logically makes sense. Yeah.
Correct. So if we have a system where we have four strings, I mean,
you times it by 4.
Oh, yeah, you got it.
Yeah, I get it. Yeah. Because there's four strings, four things acting on it.
It's called rack and pinion. So you have four strings in there.
All right.
So there are
I didn't know that was a thing.
yeah. So there are four strings, four tensions. Correct. So now you understand how easily we can solve all these questions based on Newton's second law of motion.
Yes, I do. You made that look so easy. Yeah, I was really like because you know when you look at first glance in the book, you're like, oh my god, I can't do that. It's like too complicated. But then because you showed the relation between all three of these, and you said that this was the most these three are basically the questions that they just keep rewording differently in my book, but there's like 50 of them. But because the principle and correlation between all three is the same, it's a few tweaks here and there, and it's logical. It's nice and easy. So I like that. Yeah, that even with something I haven't learned, with the full one, I know. So, yeah.
So that's it. And next time, actually, in the next class, we'll introduce to you the coefficient of friction. So in all these examples, we are avoiding friction, right? Friction is an additional force which is acting in the opposite direction, just as we are having tension in this particular case. We'll add friction to it. And then we'll do questions related to your next topic, which relates to coefficient of friction. Is that interesting?
Yes, yeah, it definitely is. Wait, so with friction, do they specify in the question, or because we always assume that there isn't any, but when with questions where they say friction, is it actually said in the question?
They will tell you mu is the friction and it is 0.05. Friction is a constant number and it is between two surfaces. So depending on the surface, we have different friction constants. Coefficient of friction, it is called. So we'll take that up in the next lesson, okay?
That sounds interesting. Okay. So thank you so much, sir, for your help. I really enjoyed that, like especially that last slide. It's going to be a lifesaver. Going to remember that table when I go in the exam. That's really helpful. So thank you so much.
My pleasure. Have a great weekend. Enjoy your day.
Yes, you too, sir.
Thank you.
Bye, sir. Thank you. Bye.